let's go ahead and get started. You can grab your stuff after I'm done. Okay. All right. So today what we're going to do is we're going to continue talking about capacitance. I'm going to start by doing. Let's go ahead and settle down and get started. So I'm going to start by doing the last problem of the homework. And the important thing when it comes to calculating the capacitance for these systems, it's really always the same. We say that the capacitance by definition is the ratio of the charge to the difference in potential as an absolute value. And the reason why I have this absolute value here is just to make sure that capacitance is positive. It's by definition a positive quantity. So for any system, whether it's parallel plates, whether it's spherical shells, whether it's cylindrical shells, the game is always to just find what the difference in electric potential is between those two conductors, and then take the ratio of the charge that's on the conductors to the difference in electric potential. So for the question that I gave you in the homework, we were to consider a system where we have some spherical shell of inner radius A and thickness T, and some second spherical shell that's concentric with this that has some inner radius B and some thickness T. And I put some charge plus Q on here, and what we want to do is we want to find what the capacitance of this system is. So as I said, the first thing that we want to do is write down this definition of capacitance that tells us that we need the difference in electric potential ultimately between the two plates, or the two shells. And so in order to find this difference in electric potential, what we can say is delta V is going to be equal to the negative integral of E dot dl from some inner radius we can call R1 to some outer radius R2. And from this equation what we can see is we need to know what the electric field is. So then to find the electric field, what we're going to do is apply Gauss's law. So the integral of E dot ds is going to be equal to Q in divided by epsilon naught. Now, since we're only really interested in the difference in electric potential between the outer portion of this shell and the inner portion here, there's only one region that we have to find the electric field. So it's going to be this region here. So as with all of the spherically symmetric Gauss's law cases, this left-hand side is just going to end up being E times S, which is going to be 4 pi R squared times E. And then the charge that's inside this Gaussian surface that I drew in this region is just going to be the charge capital Q. So this is going to be equal to capital Q divided by epsilon naught. We can rearrange this in order to solve for what the electric field is, and so that says that E vector is going to be equal to 1 over 4 pi epsilon naught Q divided by R squared times R hat. Okay, so we're a third of the way there. We've gotten our electric field. Now we have to find what the difference in electric potential is between this inner surface and this outer surface. And that's just to take this electric field and then plug it into this definition of the difference in electric potential. And so when we do that, we say that dl is going to be equal to R hat dr. And then plugging this in here, we're going to have the integral of 1 over 4 pi epsilon naught Q divided by R squared. R hat is 1, so we're left with a dr here. And we're going to integrate this from A plus T, because that's where we're starting here, from A plus T to B. And so this is going to be delta V. Okay? So when we do this integral, we see that everything right here is a constant. So we're integrating 1 over R squared dr. That's going to give me a negative 1 over R. So negative negative becomes a positive. So this is going to be equal to 1 over 4 pi epsilon naught times Q. Well, let's put the Q right here. times 1 over b minus 1 over a plus t. Okay, so this is a little bit of an unnecessary step, but I like to do it so that I can check the units in the end. So I'm going to find a common denominator here and then rearrange this. And so when I do that, I multiply this by a plus t over a plus t. I multiply this by b over b. And so what we see is this is going to be equal to q divided by 4 pi epsilon naught a plus t minus b divided by b times a plus t. Okay. Now, when we look at this, we can see that this is going to give me something that's negative, right? Because a plus t is going to be less than b, and I'm subtracting b from that, and so this is negative. And so in order to make this positive, I can reverse this, so it's going to be b minus a plus t. So then the magnitude of delta V is just going to be Q divided by 4 pi epsilon naught B minus A plus T over B times A plus T. And then we've completed this second step. So, there's a question? Yeah.
Could you talk a little bit about the limits of integration? Because I was not sure whether to integrate from you know, from 0 to A and 0 to B, and then subtract them, or from because of the shells, I was
okay. Sure. So you could have defined this integral to go from 0 to b plus t if you wanted to, but the reason why I did it just from a plus t to b is because the electric field in this region is 0, the electric field in this region is 0, and the electric field in this region is 0.
You can just integrate between the two surfaces.
Exactly. So per taking differences, because I was a little bit cavalier with the way that and lazy maybe even, with the way that I defined the electric potential function as an indefinite integral, and I just kind of willed the constant of integration away to 0 by saying that depending on where you're defining 0 to be, that constant will be 0. When we're doing calculations like this, we're not finding the electric potential function, we're finding the difference in electric potential, which means that we want to do a definite integral, and by definition this delta V is going to be delta V between the two surfaces of
Even if we did them separately and subtracted them, your constant would be the same.
Yeah, ultimately, yeah. Other questions? You seem like you had one.
I just had a question about how you just automatically knew this Q in that region, because I thought like the Q was in the center, so like where A is.
So I mean this might have been partial. Do I have it written out here? I might not have defined this as well as I could have. Yeah, you just have to be careful reading it. So in the last portion I say if a charge plus Q is placed on the inner shell. So that the single preposition on is the important part here. That when I say it's on the shell, it's not spread evenly over, but it's spread on here and it's allowed to move around because it's a conductor. Okay. Yeah. Okay, other questions? So we're almost there with this calculation. So we've found what the magnitude of delta V is. We just need now to find what the capacitance is, and that's just to take the charge and divide it by this magnitude of delta V. And so that tells me that the capacitance is going to be equal to 4 pi epsilon naught times B times A plus T divided by B minus A plus T, right? Because that's just to invert this fraction that I have here, and then is this something on task, guys? We need to make sure that we're paying attention, or at least not talking, because it screws up my my flow. Okay, so this is the capacitance that we have for this system, and like I said, the process is going to be exactly the same whether I'm doing this with parallel plates or whether I'm doing this with spherical shells or cylindrical shells. So the next thing that we can talk about, and what the classwork today is going to be, is what happens if I put another shell on around this, or another shell around this? This gets to the idea of how we add capacitance. And so you might have seen in some classes you've taken in high school or previously, that if I have capacitors in series, I can add them together like this. Who's seen this equation? Yeah, a lot of you guys. We're going to actually explore where this equation comes from, because the way it's treated a lot of times is like, well, if you have capacitors in series, you add them together like this, and that's it. But we want to see exactly why this is the case. And so in order to do that, what we're going to do is we're going to calculate the difference in electric potential between this surface and if I have another shell around the outside here, this surface and this surface, and then apply this definition of capacitance, and what we'll be able to obtain is identically this equation. Now, to give you some context in how you can think about this in terms of circuit diagrams, what this really says is if I have some battery or some source of potential, and I want to add these together, this can be written equivalently as another circuit that only has one capacitor, where that has some capacitance of CEQ. So it's really a matter of saying, I have the system where I have two, I want to write it in a way that I have a system with just one. Okay? Any questions about this? Okay, so go ahead and get started on the work for today, and I'll come around and answer questions as you guys have them.